All right. Hello at home, sugars. All right, here we go. So we're on page 8 of the packet. Page 8 of the packet. And like I said, I haven't even covered anything. I'm just going to go through. I want to show you guys. We're going to label some stuff. Okay, I'm going to label some new stuff that we haven't worked with yet. And we are going to do a confidence interval for beta. So remember, we had this little formula, y equals a plus bx. Now, obviously, that was an estimate, and it would change for every single one of my samples that I took. I would get a different y equals a plus bx. So now what we're trying to do is we're trying to come up with the true population slope, which we're going to use the Greek beta for, okay? All right, so we're going to go ahead and label a few things that you'll have here. The first thing, do y'all remember which one of these is my A value? Do y'all remember? No. All right, so we had A plus BX. It goes in order. A is first, B is second. Okay? Now remember, I told you A is not very important right now, but B is very important. We are going to use B in this situation, okay? For you guys to know, this problem is about helicopters, and you taking the helicopters and the flight time that it takes for the helicopters to land, okay? The sample size was 70, so I want y'all to just write that right over here. The sample size was 70, so we took various different size helicopters and we dropped them. We used to drop them from the stadium, the highest point on the stadium, and we would drop them, and we'd have different ones. So they'd be weighted down with 1 paper clip or 2 paper clips or 3 paper clips, and then we'd drop them, and then we would graph that. Okay, so we would have a scatter plot. And so what we're trying to do is we are looking at flight time, and on this one they're doing drop height. So did you do it from this many feet in the air or this many feet? We did it a little bit differently, but regardless, this problem is flight time versus drop height, okay? All right, so that's what I'm looking at. I could write an equation right now about my y hat, and that would be negative 0.03761 plus, this is teeny tiny, 0.057x, okay? Now x, and then we have y. So which one's my explanatory and which one is my which one's my explanatory and which one is my dependent independent? Help me out with that. I have a response and I have an explanatory. Okay, here are my two things, flight time and drop height. Which one is affecting the other? Drop height is going to be the explanatory and will explain how long it flies. Are y'all good with that? All right, so I'm just going to write that at top. This is stuff from chapter 3. So I'm going to say drop height is my explanatory. And then flight time is my response. All right, is everybody good? All right, so now what I'm trying to do is I'm trying to use my sample data. This is what we've always done. Use your sample to try to make some sort of inference about the population. All right, so this is our confidence interval. Are you ready? Okay, so we're trying to capture our unknown population beta. It is B plus or minus. Now B, because that's my sample data, right? That's my sample slope, and I'm trying to capture my unknown population slope, which would show a relationship between my X and Y. All right, T star. And the standard error, which we always put right there, right? Standard error. But this is the standard error of beta, okay? So it's SEB, SE subscript B, which they give you on a computer printout, which is pretty stinking awesome. So notice that this right here is like my row for the slope. That's my beta row, right? This is my row for the slope right here. And right here it says standard error of the coefficient. Well, this is coefficient B right here, right? So this is the standard error of B right there. So it's in the standard error column, and this is my row for my slope. So this right here, let's go ahead and label it, is the standard error of beta, right there. So we're going to use this We're going to use this, and we're going to come over here and use that. All right, so there are many things that are important in this, but do y'all realize that there are two variables? This is a two variable analysis. A lot of times we've just used one variable. So remember when we did degrees of freedom, it was n minus 1? Okay, and that was because, remember, every time we have to estimate and use a sample piece of data, you have to give away 1 degree of freedom. Okay, and that's the way I thought about having coins, right? So I collected, if there's 70, I collected 70 coins, but I have to give one away if I'm using a sample to estimate. Well, guess what? I'm using two variables here. Isn't this two variable analysis? I have an X and a Y, right? So since I have two variables, I have to give away 2 degrees of freedom. So this is an n minus 2. I think this is maybe the only time that that happens. Degrees of freedom is n minus 2. So our sample size was 70. In this example, they flew 70 helicopters. So 68. All right, so now all we have to do is plug it in, plug it in. So my B goes right here. My standard error of B goes right there. But I do have to find my T. And they want us to do a, what type of confidence does it say? 95% confidence. Down in the notes there. So we're doing a 95% confidence interval. All right, so get out your sheet. So our degrees of freedom, we're down at 68 degrees of freedom. And we're at 95%. So these are the two things that we're going to use to look it up. So first, I want y'all to go to 95% at the bottom of table T. And then we're going to go up to 68 degrees of freedom. But can we go up to 68 degrees of freedom? No. So which one of these numbers do I have to use? 60. And I can't do this in the calculator, y'all, because they have to give you data to be able to do this in the calculator. So I'm going to have to use 60 there. So I'm going to go to 95 right here, and I'm going to go up to 60. So I'm at 60, I'm at 95. What is my T star? 2. I love a good problem, right? So do y'all see that? It's at 2? All right. So now we just have to finish the problem out. So I know that my T star is 2.000. All right, plug it in, plug it in. So sometimes your B is very, very long. Just write the whole thing. Suck it up. It's not a big deal. They gave it to you. You didn't even have to find it. Just write it down, okay? Plus or minus 2.00. And then your standard error, do not round. Just write the whole thing in there. 2018. Boom. All right, I suggest you find your mho first. And I got, whoa, what'd y'all get? That's ugly. 4.036 times 10 to the negative 4. Is that what y'all got? Anybody get that in their calculator? I can't write it like that, y'all. I'm going to have to go ahead and change it to a decimal, okay? So what does that negative 4 mean? To move my decimal what? 4 times. So that means I need to put 3 zeros in there, okay? So what I really have there is 0.0004036. That's my mho. And if tediously long decimals is what you have to deal with today, bless your heart, we can do that, right? We're fine. Now all you have to do is split it up and you're done, okay? All right, so let's go ahead and do the minus version and the plus version. So I'm going to add. And make sure that's what I got. Yep. .005. All right, good? Did y'all get those numbers? Okay, so just happens to, we could be dealing with large numbers, we're dealing with small numbers today. All right, so I am, this is your decision, 95% confident that the unknown population slope, beta, gosh, right here I have to say two things. Obviously I have to say the numbers, but I also need to say what the slope is relating, okay? I'm going to do that right now. Relating flight time to drop height. Doesn't matter which way you say that, by the way. Falls between .00533208 and .006128. Now, to make that even better, I could say if that is in like feet per second. I don't know what exactly the measurements were on there. If I went back in the book, I could read it and see, but we're going to leave it right there. All right, does that seem too hard? Is that okay? Are y'all good with that? So now we're just trying to capture beta. There you go. All right, so now we're just trying to capture beta. Obviously, there's got to be more than that, right? The only thing that's going to be different here is the setup. You just need to name that you're doing a confidence interval for beta, okay? We'll do Hose and Haas tomorrow. The conditions, we're going to look at one problem together. We're going to do one more completely through where you can use your calculator, and on that, we're going to check conditions, okay? All right, so I want you to flip back to page 4. I want you to flip back to page 4. And we're just going to look at conditions real quick, okay? We're going to look at conditions. Now, we are doing a linear equation, right? Linear? Yes? Okay. But I told you that A wasn't very important, right? Did I tell y'all A wasn't very important? Okay. So what we're going to do to check our conditions is liner. And I know you think I spelt it wrong, but didn't I say A wasn't very important? Get it? Linear. I took the A out. Okay. All right. Did you get that? Anybody? Okay.
I got it.
Okay. Thank you. All right. So the very first thing you need to do is if they give you data, you need to check that it's actually linear. That's really important, okay? So if they give you data, so if data is given, I want you to examine the scatter plot to make sure that it's linear. You can also look at the residual plot, and remember the residual plot, my redneck way of saying it was no pattern equals good fit and line. Do y'all remember me saying that? Probably said it once or twice in here, okay? So remember your residual plot, no pattern equals good fitting line. That means that a line is a good fit for the data. Not an exponential curve, but a line is good fitting line. Okay, so that's kind of from chapter 3, right? Okay, independent. Look at how the data was found, okay? Was it random sampling? Was it random assignment? That helps us ensure the independence of every observation, okay? So making sure that. Obviously, you can always check right here the 10% condition, okay? So if it's done without replacement, check to make sure the population is at least 10 times the size of the sample. So we know this independence rule. All right, so we have that. Normality, what? I thought we were doing a line. Where did normality come from? Okay, imagine this. Imagine this. Imagine this. Y'all ready? Here's my line. Here's a bunch of different dots. Okay? Now, we talk about residuals, but do you remember what a residual is? It's the distance, right? Do y'all remember? So it's this distance right there. And that's a residual. That'd be a -1. That'd be a positive residual. So really, the residuals are very important to creating your slope, aren't they? Okay, and remember how we find the least squares regression line? All the residuals add up to 0. And so really, your residuals are a very good reflection of the slope itself, okay? And so what we're going to do is we're going to make a normal probability plot is my favorite, so I'm going to highlight that. I like to make a normal probability plot of the residuals to make sure that my residuals are approximately normal, okay? That means my spread is approximately normal. We have some down here, we have some here, most of them are in the middle, right? That would be a normal distribution. So I'm going to show you how to do that. It's not very hard, but before I even get residuals, I'm going to back up because we're talking about residuals here. To get your residuals, do y'all remember there's a list with residuals in it? There's a list with residuals. Before that list is there, you always have to stat calc 8, and that will create the residual list in your calculator. So if you're given data, you have to stat calc 8, L1 and L2, and once you do that, that will create your resid plot. That will create your resid list for you in the calculator. I taught you that a long time ago, okay? All right, so we have all these residuals right here, and we just want to make sure that they are spread out normally against that we want to make sure they're approximately normal. So we're going to use the normal probability plot. I'll go through that with you, okay? All right, now this one's crazy. It's called equal variance, and all this is we're going to look at our residual plot, and we want to make sure that they look like the scatter is roughly the same from the smallest and largest x value. You don't want it looking like this. Like this is a bad version. Okay, does it look like my scatter plot right here? The scatter is roughly the same from my smallest x to my largest x? No. Okay, so that right there would not be equal variance. What we want is, again, we want it to be roughly, obviously no pattern, but we want the spread, if you will. Variance means variability, spread, right? We want the spread to be about the same from the smallest x value to the largest x value. So this one's good. This one is not good, okay? So you don't want the variability to increase or decrease substantially, okay? Obviously, there could be some outliers, but overall pattern looks pretty consistent, okay? And then random, yes, we got to throw our random sampling or SRS down in there, okay? So liner, that's what we're doing right there, is liner for our linear. Remember, A is not very important, okay? All right, we've got one example, and then we are done for the day. I want you to go all the way to page, probably 10, page 9. Page 9, get out your calculators. So we did this a long time ago. This is not your page. This is an updated book. But, so we did this, probably this example. I know it's on my notes. Does fidgeting keep you slim? So NEA stands for non-exercise activity. So if you had a lot of non-exercise activity, like you're like this all the time, you know what I'm talking about? Those people that you sit with at the table and they drive you crazy. You know what I'm talking about? Okay. So if you had not a lot of non-exercise activity, look right there, okay, then you had more fat gain, okay, is what I'm thinking, than if you burned a lot of calories doing non-exercise activity, then you didn't gain as much weight, okay, is kind of what we're looking at. So what we're going to do is we're going to look at this. They did a scatter plot for you. I want you to go ahead and put the data in anyways, because I'm going to show you how to do it in the calculator and not just by hand. We could do it by hand because they did give us a computer printout, so we could do the exact same thing we just did. But I do want to show it to you in the calculator, okay? All right, and we are going to go through the conditions, the liner conditions, okay? All right, this is only 2 set data, so put all of NEA, both rows of NEA and L1, and both rows of fat gain and L2. Is that your question? Yeah, it's just a lot of data. All right, so I have 16. So you should have 16 pieces of data. Remember, is it important that your X matches up with your Y? Yes, because that's one human. Remember that you don't want those to be those to change around. So put everything in L1 and L2. Speaking of non-exercise activity and fat gain, having my own personal summer up here.
You should just step outside for a few
I need to teach from right there. I need to teach from right there, for sure. I feel like I just did boot camp. I do need to show Eugene and Owen, though, my super cool running shirt that I have on underneath this. It says run, but it makes the picture of a Santa Claus. It's from Dragonfly in Noonan. It's awesome. All right, do we have our data in? So first thing we need to do, we're going to do liners. So we're going to do linear, and we're going to do this all together. So you probably have room at the tippy top of your paper. So let's do L. And L means linear. Is your data linear? That's our first thing. Liner. It's like I took out the A in linear because your A value, your y-intercept's not that important. All right, so is it linear? How do I find out if it's linear? Do y'all remember? Do you remember how to graph a scatter plot?
Yes.
Second, stat plot. This is a good review for your little final exam. So I'm going to go here, and I'm going to do a scatter plot. It's your very first one, and it should say L1 and L2. And then zoom what? Zoom 9. Good job. Did y'all get that? No? Wait, what?
That's what I got.
All right, so we're on a scatter plot, L1, L2. Yes? Okay, now zoom 9. And tell me if yours looks something like this now. No? Not at all? No? Let me come check. No? Did you just do that first row? Okay, are y'all good? Good?
It says I'm errors. I've been saying this for like months, and I'm just not asking.
We are with the nerve. Go to. Let me see what it is. Oh, look what's in your y equals.
Yeah, that probably is.
Yeah, delete those out. All right, are we good? Does it look somewhat linear to you guys? Does a line look like the only thing that could possibly explain this? Yes, let's go with it. Sure, a line. Okay. All right, so yes, it does look approximately linear. We can fit a regression line to it. The next step, even though it's not in your conditions, you need to go ahead and stat calc 8, because as soon as you stat calc 8, the residuals will be stored in your calculator. Okay, and we're about to have to start looking at residuals. So stat calc 8, L1, L2. You do not have to store your regression equation, but I'm going to, just so we can see it. All right, so here is our data right there. So we have an A value that's really not that important, but here is our slope. It is a negative slope, okay? Now remember what we're looking at here. X is your non-exercise activity, and then Y is your fat gain. All right? So as your NEA, your non-exercise activity increases, wouldn't your fat gain decrease because you're burning calories, right? All right, so the calories here, since you're burning calories here, then your fat gain should go down, and so that's why we have a negative slope, okay? All right, so good to have that out of the way. And now, would you, this is another one, oops, sorry. When you do the independence, you can look at how the data was produced. Do you feel like all of the people in this random sample, if you were to go back and read this, do you feel like everybody's non-exercise activity, calorie burn is independent from each other. I would say absolutely. So we can go ahead. You can do, if you wanted to, you could do this rule right here for all of our human beings that have non-exercise activity. I don't feel like we necessarily need to do that, but we can. All right, so this was about healthy adults. So if I wanted to look at this, we could say the population of all healthy adults is greater than 10 times, what do we have, 16? So yes, that is true. And I would say that all healthy adults would be independent of each other, and you could definitely say that, okay? All right, so now what we need to do is N. So if you go back to N is talking about the normality of residuals. All right, so normality of residuals. I want to use, you could either use a histogram here, but we don't have a whole lot of information. We only have 16 pieces, so a histogram might not be the best. You could use a box plot, couldn't you? To see some symmetry, but I like to use the normal probability plot. So I'm going to show you how to use the normal probability plot today, okay? If you look down here at the bottom of the paper, they did a histogram of the residuals, which looks roughly normal, okay? I'm going to do a normal probability plot. That is my preference. So here we go, normal probability plot. Go back to second y equals, go to stat plot. Your normal probability plot is the very last one. Go all the way down to the bottom. All right, and then it's asking you, what data do you want to do the normal probability plot of? Residuals. So you need to go grab the resid list, which is under list. Do y'all remember that? So go to second and then go to list. And grab your residual plot. Oh, look, I have NEA and fat gain in here already. All right, so go to resid. And, oops, apparently I didn't go to the right place. Sorry. Go to resid right there, second list. Resid. So now it should say normal probability plot. It's your last one. Remember, if it's normal, your normal probability plot will be approximately what? Look at it. Linear. Okay, so it'll be linear. All right, so what we're going to do is, now that I have residual, I'm doing the normal probability plot of the residuals. And you can zoom 9. And does my normal probability plot appear to be approximately linear? If it does, then that means my residuals are have approximately a normal distribution. So it does, normal probability plot does show a linear pattern. If y'all don't like this way, y'all use one of these other two ways. Shows a linear pattern, so my residual are approximately normal. Good. Easy. All right, this is equal variances. All you have to do is look at your residual plot to see how equal everything looks. How equal of a spread is it? Is it equivalent, equal scatter? Look at your residual plot and look for equal scatter. So now we're going to go look at our residual plot and look for equal scatter. All right, now we have to do a residual plot. Y'all ready? Second y equals. And they have one on the paper for you. Residual plot, you do a scatter plot, and it's L1 and resid. Scatter plot, it should say L1 and resid. Just in case you don't remember that. All right, so we're just going to make sure this is our residual plot, L1 and resid. We're going to make sure that our residual plot looks like it is equally spread all the way across. Zoom 9. Zoom 9. All right, so does it look somewhat of an, well, there's equivalent spread across? What do y'all think? Actually looks like it's going out back in though, right? But if I took away that 1 point, would it look pretty spread out? Yeah, so it might just be that we have an outlier right there, but overall, if I can cover up one point and say, yeah, it looks like a pretty equal spread, then it is, okay? So give it a little bit of credence there. Don't be like, y'all know how y'all were at the beginning of the year, right? Y'all saw one thing and you're like, that's an outlier, that is skewed. And I'm like, it's not really skewed, okay? So that does look like equal variances. So we have equal spread. Put a check mark. And then, is it random? Yes, this did come from an SRS. I know that doesn't show it anywhere unless you read the book. Okay, it did come from an SRS. All right, how do you do a confidence interval then? Can I use this beautiful computer printout to do it? Absolutely, but you can also do it in your calculator if they give you data. So go to your calculator and figure it out. I want you to do an interval. Go, do an interval in your calculator. Stat test. All right, which one do you think we need to pick?
Linear regression, T.
Okay, we're never going to do analysis of variance, which is really a cool class. Y'all need to take it in college. Totally cool. Okay, so analysis of variance, very fun class. We are not doing a test. We are not going to do F-test in here at all, so we are not going there. But we are going to do ln-reg t interval. Okay, ln-reg t interval. So go to G. Your data's in L1 and L2. They wanted us to do I know I didn't tell you this, so write it at the top of your paper. We're doing a 90% on this one. So if you did want to go back in the book and look at this, I believe this problem's in your book. We're going to do a 90%. You do not have to put the regression equation in. How cool is that? Don't even worry about it. Skip over it. You don't have to. And press calculate. And it gives you, it gives you your slope, okay, which is dead center in the middle, your B, okay? And then this is going to capture the unknown population slope relating NEA to fat gain. So I'm 90% confident that the unknown population beta relating NEA to fat gain falls between negative 0.0047 and negative 0.0021, okay? They do give you some extra information here that you might need to know. I do want to point out one more thing for you, and then I'm done, okay? Because we will need this little S right there. We're going to need that later. That is not SEB. That is not the standard error of beta. We are going to use little s, which I'll talk to you about. That's the standard deviation of the residuals. We're going to use that later. I do want you to recognize that that little number right there, do y'all see that 73985? It's right there. See this little s right there, that 73985? This is the standard error of residuals. It is not the standard error of beta. It is not on the line where beta is or your B value is. We know that this is all your B information right here. Okay? This is not on that line. This is on really your R squared line. So it's the standard error of your R, your residuals, okay? And we will use that tomorrow with our test, okay? All right. No homework tonight. And you will have one confidence interval problem tomorrow in class. Tomorrow is a study hall in class. Friday, I'll do the significance test with beta. Good? Capiche? All right. Good job, y'all. Make sure you turn in your multiple choice packet today and turn in your homework from last night, okay? To the printer before you leave. Bye, y'all.